So from your first step as a child, you've been doing physics experiments, from first pulling yourself up on the chair, to standing up, crawling, to cruising down the hall, finally figuring out how to walk on your own, run on your own very quickly. That's why children, they don't learn to walk, they learn to run, by the way. You've been doing a lot of physics experiments with the friction of the floor, with the capabilities of your own limbs to get you around, with gravity, of course. You then moved on to more complicated experiments, trying to learn to throw the ball, to catch it, to predict from a little bit of information about its initial flight, where it's going to land. If it's a wild throw, maybe you have to adjust and get to it. You learned to anticipate where that ball was going to be, so you could hit it with your racket in this case, or your bat, or your foot, or your head, or get out of its way, or make it go exactly where you want it to be. So you've done a lot of physics experiments. So why is it everyone says physics is hard? You've heard people say this. They get to their high school physics class. Now, here is the point where this might not be the crowd this was pitched for. You might have enjoyed physics quite a lot. But you know the sentiment. Everyone says physics is hard. And I submit that the reason we like to say physics is hard was this. They put math in physics. Your science class, okay, you could identify where the frog's heart was and follow the little blood vessels in there and color that. That was easy. But then we went and put math in your science class. So physics is hard. Something else I wanted to say, sorry. I had this all going well last week. Okay. Oh, I know what I wanted to say. I had something else for you guys. So this crowd, am I right? Most people also said they don't like story problems. And probably a lot of your friends in school said this. Is this the crowd that actually liked story problems? I mean, because I thought so. Because, not only did you get a little math problem to solve, you got this little puzzle you got to figure out, right? They're a lot of fun. Is that my crowd here? Okay. That's what I wanted to say there. Okay. We actually like to teach this equation. You know what this means. And even if you haven't taken a lot of physics classes, which I know a lot of you have, force equals mass times acceleration. That's not how we like to teach it these days. And if you remember enough from algebra, and I think you all do, you see that I just divided both sides by m and then switched them around. And the reason we like to do it this way is because the stuff on the right side is generally the stuff you can control, and over on the left side is acceleration. This is something you observe as a result. So if I increase the force, I should expect a larger acceleration. If I decrease the force, I should expect a smaller acceleration. Likewise, if I make a larger mass, acceleration should go down, okay. And a smaller mass, acceleration should go up. So let's do that. Instead of the way we start out in physics class, let's do it the way you first learned it. With ordinary objects, just stuff you can touch. So an ordinary sponge here, perfectly normal. I don't have to explain what that is. You know what that is. And I have a hammer. So I'm going to use the hammer to apply a force to the sponge. And we should expect that when I do that, we observe an acceleration. Very good. All right. So let's try this. This is the interactive part of the demonstration, by the way. Sarah, you ready?
Oh, God.
Put your hands up. All right. So that was a fairly large acceleration. I have here another ordinary object, a block of wood. You can probably guess that the block of wood is heavier than the sponge, and you would be right. So same force, same hammer. Going to apply it, try to aim it right here between the aisles. Going to apply that same force to the wood. And other than bouncing off the table, it didn't go quite as far. All right. Next I have this, which is not quite an ordinary object. This is a lead brick from the nuclear physics lab. It's very heavy. It weighs 30 or 40 pounds. How many of these things weigh? Were they 50? We had to ship them. Yeah. They're crazy. So maybe not quite an ordinary object, but you would predict, knowing that as the mass increases, the acceleration gets smaller, we should observe a much smaller acceleration. So ready for this test? Which way should I aim it this time? Okay.
Away from us.
Straight toward us.
I think it's coming right at Sarah. Let's see. 3, 2, 1.
And the darn thing doesn't even move.
And it doesn't even move. And that's actually what a lot of people see. So let's try this a different way.
Rather, it's not that it doesn't move, it's just infinitesimal.
It's a small acceleration. But momentum is still conserved. So the momentum from this hammer is still transferred into this. All right, so let's try this a different way. I'm going to take that, I'm going to balance it up on my hand.
Oh, can I swing?
Sure. And rather than applying that force in this direction, I'm going to apply it straight down. All right? And when I do that, because you all thought I was going to do this, right? My hand is just fine. It was moving. It's moving slowly. It had a small acceleration. My hand is able to absorb that because it's a little cushiony. It has some time to exert that force. So what a lot of people think they see is just exactly what Sarah said. The brick simply stopped the hammer. So to prove that is not the case,
Well, it didn't stop. Just absorb the impact.
absorb the impact. But a lot of people have told me it looks like it stops. So I'm going to take this, another ordinary object, test tube. You've used these in chemistry class probably. And since I know what's going to happen, I'm going to wrap it in paper. That's not to hide it. That's actually a safety precaution. And you can see the test tube is strong enough to support the weight of that brick. And good lab safety suggests I do this too. All right, and I'm going to apply that same force, cause that same acceleration to the lead brick, and see if we get a different result than when my hand was under there.
Yep.
And you can hear we clearly got a different result. Let's dump that in my magic repairing fluid. There it goes. Okay, I'm just kidding about the magic. So there's no magic involved in here. This is all science. So everything here is science. The brick was really on top of my hand. It really is heavy. I really did hit it. It wasn't a fake hand. This is not a fake table or anything. This is all science. All right. When my kids were in the 4th grade, this was a review question in their science textbook. It takes a lot of blank to stop an airplane. So let me back up there. I always thought it would be fun to be the science dad, because I know a lot of stuff and I can tell my kids things and explain a lot, and I was sure they'd be really impressed. Here, I need some lights down, and that one, okay. And I knew they'd be really impressed. So they'd have a good, we're talking a little bit vocabulary here on these words we use for science. So they had this early on, another question. The lesson was about transparent, translucent, and opaque. These are 3 scientific classifications, and they were learning to use them to describe, is the glass transparent, is the paper opaque, some light gets through, the tabletop is completely opaque, so that's maybe translucent, which are great things. And so they'd ask me questions about this science lesson, what is it? And I said, well, it's really interesting, because you'd think like the water in the glass here is transparent, and I have this blue laser pointer here. I can shine it through. You see it scatters a little bit, but most of the light goes through. Same with the glass here. Light just goes right through it. But if I take this cooking oil, and I shine that light, if you can all see it, you can see it starts out, do it over, how about here so you can all see it. So it starts out at the top, it's really bright, but as it goes down to the bottom, you can see it kind of extinguishes and gets dim. It's actually even a very different color, right? So the oil is fluorescing with this wavelength and blocking the blue light, which is one of the reasons it appears yellow. And apparently, if it's fluorescing into green, you're taking that blue light, you're turning it into green light, which should enhance the stuff near yellow, I guess. So is it transparent or is it opaque? Well, to the blue light, it's kind of, after some distance, it's completely opaque, but it's sort of translucent. Now, my kids, of course, react to that with their own questions, which is usually something like, Mom, can you help us with science homework? All right, so much for being the cool science dad, right? Get all my lights? One more. There we go. All right. It takes a lot of blank to stop an airplane. So what would you put in this blank?
Courage.
Courage. So I brainstormed this. We'll see if we get back to answers like that. Takes a lot of runway to stop an airplane.
All right, good.
I mean, yeah.
In the traditional landing, we like it this way. Plane comes in slowly, bounces once, and over, what's a runway, mile and a half? They can stop shorter, 2 miles. Comes to a stop slowly from a landing speed of like 300 miles an hour down to stopped at the gate or at the end of the runway. And that's true, but being a science question, is that always true? We want to ask that, right? So you know, if we did this rather unhealthy landing path, you come straight down, you're going to come to a stop right here and not use any of this runway.
I mean, you might blow up.
But you stop here.
Yeah.
But it still stops. So runway isn't perhaps the complete answer. It's maybe the better way to land a plane, but not quite. Takes a lot of trees to stop an airplane.
Yeah.
Now, you can imagine a big 747 coming in. It might take out a fair chunk of the forest. But you know how they build airplanes. They tend to be lightweight. Collisions with trees aren't usually very healthy for the aircraft. And while it may not come to a stop right next to that tree, probably it's going to come to a stop not far from there. All right. Mountains, also for the same reason. Now, a big mountain range may cause you to want to go around and change your flight path, but a single mountain is going to bring you to an abrupt halt. Okay, it takes a lot of chickens to stop an airplane. Now, here I imagine chickens lined up on either side of the runway with little lassos, right, trying to latch on. You didn't imagine that? Okay. But with enough chickens, it could be a lot of chickens, it would bring the flight to a halt.
A couple carefully targeted chickens in the engine.
And that was my other thought. If you were Captain Sullenberger on flight 1545 out of, was it Boston? New York. A couple of geese into the engines will send you landing in the Hudson River after not too long. So here, it takes a lot of courage to stop an airplane. There are a lot of other things we might use. Let's see what I had something similar. Nerve and chutzpah. I like the word chutzpah. Those are nice, and for a literature class, that might be a good fill in the blank here. But this is science class, and that doesn't seem to be really the science subject. So let's go back to the science words. It takes a lot of time to stop an airplane. Again, in the traditional landing, it's a couple of minutes down the runway before you come to a nice safe stop. In the unsafe landing or the mountain collision, it's really a very short time. All right. This, unfortunately, is the answer that the 4th grade textbook wanted you to give. You had the same 4th grade textbook, by the way. You were in my son's class. Takes a lot of force to stop an airplane. And that's not quite the right answer because, in fact, for the reasons the chapter gave, it talked about the problems of an icy runway and how on an icy runway you have less braking force. You're going to take more runway to stop, you're going to take more time. So it really is the combination of these things. So the combination of time and distance, runway, we call work, and the combination of time and force we call a change in momentum. So let's see, here we go. This is really just another form of Newton's second law. So delta P, as long as your mass is not changing, that's just m delta V. If you take the delta T over here and divide it, you see you've got ma on that side. But in this form, it's more a statement of the impulse momentum theorem. So the total change in momentum is going to be equal to the force applied over time, or the average force over some time. But I want to do this with the board. All right, so in this experiment, you've all done this experiment, we measured a bunch of these boards, and we find that one is almost enough to hold up my weight. And I can lean on this. Now, if I can get my hand going a meter per second, that's pretty slow. Assume I can get it going 10 meters per second. These boards, we've determined, break after they flex about 2 centimeters. So I'm going 10 meters per second. What's my delta t for the impact?
Are you assuming you can keep that speed to the collision?
Well, actually, so assuming it comes to a stop in a uniform way, then your average speed is going to be half that. So 5 meters per second for 2 centimeters is going to be, anyone got it? 100th of a second? 1,000th of a second? Something in that range? Okay, you'll believe me. So that's really small. Measure my hand at 10 meters per second, and if we assume the hand is about a kilogram. So we've got about a 10 over here, and this delta t, we've got something really tiny. So the maximum force, as it turns out, is much more than the force that the weight of my body is exerting on the floor. The force to change the momentum of my hand in this tiny fraction of a second is huge. And the board is not strong enough to do that. Okay? Thank you. So what have we learned? Science is not magic. Changing momentum requires a force. And a small force over a long period of time can have the same effect as a large force for a much shorter period of time. Good? Let's see, I need to move this out of my way. Sometimes if you want to make a large change in momentum, like with the brick, it's better to be a little flexible so that that force can take place over a longer period of time. The force is less. If you are inflexible, you end up being brittle and sometimes fragile. Right. And a large force may go unnoticed if it does not persist. If I pull really quickly on this, it actually exerts a fairly large force on these pieces of glassware. But because I run out of paper over a short period of time, the force stops. So the change in momentum to the objects here is really very tiny. But there is a change. All right, and the conclusion slide. Where's the conclusion slide? All right. If you're observant and persistent, if you do the math, if you study hard, if you take a physics class, sometimes there is some magic. How's it going? After all. See that over there? I'm drinking oil. All right. Thank you very much. Another trick in there too. Indeed. All right. Thank you.